Hello everyone, my name is Peng Gaoyan and I'm from the Hong Kong Polytechnic University. Today, I would like to give a short introduction to GNSS Integrity Monitoring. Before going to the main topic, I would like to introduce two very important concepts in integrity monitoring. They are integrity and continuity. Let's start with the integrity. In this figure, an airplane is requested to fly along the desired path. The yellow point is the estimated position, and the green point is the true position. And the difference between them is the position arrow. The airplane is not allowed to cross the boundary. In this case, integrity says that the probability of the true position being outside this red region is very small. So first, integrity can be viewed as a measure of trust in the navigation system. Now let's look at the second case. As you can see, the true position is close or beyond the safety boundary, and the red region also crossed the boundary. And integrity will say, I can detect this and raise an alarm. So integrity also means that the system can provide a timely warnings when the navigation solutions should not be used. Now let's move to continuity. It's the ability of the total system to perform its function without interruption during the intended operation. So when continuity will be lost, here are some examples. If the protection region crosses the forbidden boundary and shown here, the system raises alarm, and the nominal operation is interrupted. Here is another example. If GPS signals are lost, we may no longer have a reliable source for positioning. In that case, we may also need to abort the operation. So continuity is about keeping the service available during the operation. Here lists the requirements for different flight phases, which is copied from the VAS standards. We can see that at different stages of flight, the requirements for accuracy, integrity, and continuity are all different. Now, with these concepts in mind, we now move to the general process of integrity monitoring. In simple words, the purpose of integrity monitoring is to provide a guarantee of the correctness of the navigation solution. In general, this process can be divided into three steps. The first step is fault detection and exclusion. We start with GNSS measurements, and we ask whether these measurements are healthy or whether they contain faults. This is usually done by hypothesis testing. The null hypothesis means that all measurements are fault-free. The alternative hypothesis means that at least one measurement is faulty. And the continuity requirements decide the rejection regions. During this process, we need a statistical model, which comes from the nominal error models. So what is the nominal error models? Well, here is some common sources of errors in GNSS range measurements, such as the clock errors and atmospheric errors. Even after we apply the corrections, there are still some remaining errors, and these errors are random. A typical example of the empirical distribution of these errors are shown here in this histogram. As you can see, these empirical distributions are difficult to parameterize, and this makes them very hard to use in integrity monitoring and hard to transmit to users. So instead, we often use an overbound for error modeling. More specifically, we use a Gaussian distribution as the overbound. And the overbound is conservative. It still matches the real error behavior, and it is simple to parameterize. In this way, obtain the nominal error model. If you want to learn more about the overbound, you can check the page 22 to 42 in my tutorial slide. You can download from the email sent before. After that, we perform fault exclusion. If a fault is detected, we ask another question: can this fault be excluded? If the fault cannot be excluded, then we raise an alarm. This warns the users that the current operation should not continue because we cannot mitigate this kind of adverse impacts by this fault. If the fault can be excluded, then we move to the next stage. The next stage is to monitor the integrity rates of the system. This step also lists the nominal error models. To understand this, we go back to the example shown at the beginning. Here we translate example into the terminology used in the integrity monitoring. The boundary in this figure is called the earth limit. The radius of the red protection region is called the protection levels. One way to do the integrity monitoring is to calculate the integrity risk directly. This is the probability that the position error is larger than the alert limit, while no alert is raised. We then evaluate whether this value is smaller than the integrity requirement. And here is an alternative way. We replace the limit with protection levels in this equation and force the inequality to be the equality. Then we can solve the protection levels. If the protection level is smaller than the alert limit, then we must have the probability, we can guarantee that the integrity risk is below the required value. In practice, the second approach is more common, and details can be found in my tutorial slides. After we compute the protection levels, we compare them with the alert limit, and this is the third step. If the protection level is larger than the alert limit, that means the integrity is not verified. So we have to abort the operation because it's not safe to continue. If the protection level is smaller than the alert limit, then integrity is verified, and we can continue the operation. Now we come to an important point. In integrity monitoring, we need to consider both integrity and continuity. If we try very hard to maintain integrity, this may also cause loss of continuity. For example, if the continuity requirement is too strict, only few faults can affect systems, then the integrity is kept. However, the probability of false alarms may increase. Then the system may stop more often and the continuity becomes worse. On the other hand, if the continuity requirement is too loose, the system may keep operating even when fault exists. In that case, continuity is maintained, but integrity is lost. So the trade-off between the integrity and continuity is one of the core issues in integrity monitoring algorithms. And that is the basic process of integrity monitoring. With that in mind, let us now look at the current challenges in this area. First, the performance may vary across different GNSS constellations, so the reliability is not always the same for each constellation. Second, the effect of photo exclusion is not clear. Even if a fault is detected, it is not always easy to understand how excluding the measurement will affect the final navigation integrity. Third, for nominal error models, there are still difficulties in analyzing the worst-case scenarios. Also, the Gaussian assumptions is not always valid, especially in complex environments, such as the urban areas. Finally, computation complexity is also a major issue because some integrity algorithms become very expensive when the number of measurements grows. If you are interested in more details, I recommend these two papers for further reading. To summarize, I wish you have learned the general process of integrity monitoring through this talk. This figure may look simple, but it captures the main idea of the whole topic. Detect faults, exclude faults if possible, and compute the protection levels, and decide whether the operation is safe to continue. If you are interested, each part is worth to be studied in much greater detail. Here are the references used in this presentation. And that's all for my presentation. And thank you so much for your attention. I will be very happy to answer all your questions. And if you are interested to know more about me, you can also scan this QR code. Thank you.